Welcome to the Explainer. Today, we're diving into a true cornerstone of machine learning, logistic regression. You know, right behind the complex math of modern AI sits this absolutely incredible foundational supervised learning algorithm. We're going to decode exactly how it works and why it's still so incredibly vital today. Let's get right into it.
So here is our roadmap for today. We'll start with the naming misunderstanding. Then we'll look at how the algorithm works. After that, we'll cover the 3 types of classification, jump into strengths, limitations, and evaluation, and finally look at why this is the foundation of ML.
All right, section 1, the naming misunderstanding. Let's just address the elephant in the room right off the bat, right? Why on earth is it called regression if its whole job is to classify data? Well, regression actually just refers to the underlying mathematical method we use to fit the model. Its actual purpose isn't to predict some sliding scale of continuous values. No, it is built to classify data into distinct, separate categories.
Think of it this way. Linear regression predicts numerical continuous values. You know, like forecasting a house price based on its square footage. Logistic regression, on the other hand, predicts probabilities to assign categories. It essentially answers those yes or no questions. Is this email spam or not spam? Is the customer going to buy or not buy? Is this transaction fraudulent or perfectly legitimate?
Moving on to section 2, how the algorithm works. Let's step into the engine room and methodically walk through the 4 steps of how this actually plays out, using a classic email spam detector as our example. Step 1, collect data. We need labeled data, thousands of emails clearly tagged as either spam or not spam. Step 2 is where the magic starts, learn patterns. The model evaluates input features, stuff like the number of sketchy links in the email, suspicious words, or even just the overall email length. Then, step 3, calculate probability. When a brand new email hits your inbox, the model analyzes those same features and might calculate, say, an 87% probability that it's spam, leaving a 13% probability that it's not. And finally, step 4, apply a threshold to make a firm decision. Now, the real secret sauce making all of this possible is the Sigmoid function. Let's slow down for a second here because this is the math behind the magic. Without it, an algorithm could theoretically spit out wild numbers like -400 or +10,000. And obviously, that doesn't help us figure out a percentage of certainty. So the Sigmoid function is this elegant mathematical formula that produces a really beautiful S-shaped curve. It takes any numerical output and literally squishes it down into a neat, highly readable probability between exactly 0 and 1. As the curve pushes up toward 1, the model is highly confident this sample is positive. Like, yep, that's definitely spam. As it drops toward 0, it predicts the negative class. This S-curve is exactly what makes the algorithm perfectly suited for classification. And because the sigmoid function gives us this perfectly smooth probability between 0 and 1, we typically just draw a hard line right down the middle at 0.5 to make our firm decision. If the calculated probability is greater than or equal to 0.5, boom, the model confidently assigns the positive class. Less than 0.5, it assigns the negative class. It's a really rigid, decisive boundary, but it's completely based on that smooth, nuanced probability. Now let's swap out our spam example for a high-stakes, real-world scenario. Imagine a hospital trying to predict a patient's diabetes risk. The model takes in specific patient features, things like age, weight, blood sugar level, blood pressure, and family medical history. It weighs all of those inputs, runs them through our sigmoid curve, and outputs a clear probability score. Doctors can then use that score to make mathematically backed, absolutely critical medical decisions. All right, section 3, 3 types of classification. You see, logistic regression isn't just a one-trick pony. It is incredibly versatile. The first type is binary, which is exactly what we've been talking about. 2 possible classes, fraud or legitimate, pass or fail. This is for sure the most commonly used setup across the board. But then we have multinomial. We use this when there are more than 2 categories without any inherent order, like predicting different animal species or identifying handwritten numbers. And finally, there's ordinal logistic regression. You'd use this when you have multiple categories that do have a natural specific order to them, like predicting if a product's overall quality is low, medium, or high. Because of this awesome versatility across binary, multinomial, and ordinal formats, logistic regression is literally everywhere. In healthcare, they're using it for cancer diagnoses. In finance, it's running credit approvals and flagging fraud. Over in marketing, they use it to predict whether a customer will churn and just leave a service entirely. Even in education, it predicts pass-fail outcomes. It is a massive, massive driver of high-level decision-making across major global industries. Let's transition to Section 4, Strengths, Limitations, and Evaluation. Time for a quick reality check. On the advantages side, developers absolutely love this algorithm because it's so efficient. It requires pretty low computational power, trains incredibly fast, even on massive data sets, and is remarkably simple to interpret. Plus, instead of just bluntly guessing a category, it gives you that highly useful probability confidence score. But it definitely has its core vulnerabilities. For one, it fundamentally assumes the input variables have a linear relationship with the log odds, which is basically, well, actually, to be precise, it's the natural logarithm of the probability of the target occurring. It's also notoriously sensitive to extreme outliers, which can totally skew the curve. It struggles heavily with complex, highly nonlinear data, and its success depends a lot on feature engineering, meaning developers have to spend serious time manually selecting meaningful inputs for it to even work well. And when it comes to evaluating the model, because we're looking at distinct categories rather than continuous numbers, standard regression metrics just don't apply. Instead, we have to rely on specific metrics like accuracy, precision, recall, the F1 score, and the ROC-AUC score. These metrics give us a highly detailed picture of exactly how well our model is categorizing new, unseen data and whether it's making way too many false positive or false negative mistakes. Finally, Section 5, the foundation of ML. So, where does this leave us? Logistic regression continues to play a massive role in the broader landscape of AI. Its simplicity and speed make it the ultimate baseline model before you even think about deploying more complex algorithms. Honestly, it's the essential foundation for things like decision trees, random forests, support vector machines, and yes, even neural networks. So, before you rush off to master deep learning, ask yourself, have you truly mastered the sigmoid curve? Definitely something to think about as you continue your ML journey.